Okay, everyone, let's continue with problem 2 on the wave practice worksheet. So I've already drawn a circle onto the image here. Depending on how you do this, you could insert a circle. This is actually what I did. I went to, I can actually show you here. I went up to draw in the tabs up here at the top. And over here where it says shapes, I drew the circle myself. And I kind of just winged the size of it, just made sure it fit in there. Because remember, where you draw that circle doesn't really matter because you're measuring relative distances, okay? So keeping in mind here, the speed of sound is 340 meters per second. I also copied over this little ruler. Just grabbed I Googled image search rulers, okay? And I'm going to measure the distances here. I'm going to start with the distance of the bullet. So remember, we have these formulas, the distance of the bullet divided by, actually I did it a little differently. So I have the speed of the bullet is equal to the distance the bullet travels divided by the distance the sound wave travels multiplied by the speed of sound. I know on the board it says, essentially it says the same formula, but just VB over VS equals DB over DS. The ratios are the same, right? But I just set mine up kind of ahead of time. So here, if I measure this distance, and I used a little bit of a trick here earlier to measure it really precisely. You might have to hold the Alt button when you click. If you hold Alt and use that to move the ruler around, you can get some really fine-grained movement here. But I know that the what I measured earlier, the distance the bullet traveled was, let me double check here. You can actually even see me go look at my worksheet here. This is where I do all my scratch work for this video, 3.95. So the distance the bullet traveled was 3.95 centimeters. Well, at the same time, if I put this over for the wave, it actually is very, very close to 2. It's almost on the dot the way I did it. So you see, it's a little tricky to move around the ruler here, but you can do it. You can make it work. So what I measured with the ruler for the distance the sound wave travels is 1.99 centimeters. Okay. So in this case, this is what we call a plug and chug problem. It's just plug in the numbers and chug out the answer. Because remember, if we do our known, unknown, and formulas here, we know the distance the bullet traveled, we know the distance the sound wave traveled, and we know the speed of sound because it was given to us in the problem up here. We don't know the speed of the bullet, but we do know we have this handy-dandy formula where VB equals DB over DS multiplied by the speed of sound. So I'm just going to plug those in. I'm just going to say the speed of the bullet equals 3.95 centimeters divided by 1.99 centimeters multiplied by 340 meters per second. Let's do a quick sig fig check. Thankfully, we're not doing any addition subtraction here. These two values both have 3 significant figures, the 3.95 and the 1.99. And the 340 has 2 significant figures. Remember, this 0 is not significant. So when I actually calculate out the answer, I get, it's a long number with the 6 in it, and I want to be careful here. I get 674, whoops. I get 674.874 meters per second, but I have to do my significant figures, which means that everything has to come down to 2 significant figures, so it becomes 670 meters per second, and that's the answer. My typical way of doing this is to put everything in a box, the final answer, because that's the thing I want my teacher to see. They're going to grade my work, but I'd really like them to see the answer in a big, clear box. Okay, so let's go on to problem number 3. Calculate the period of a pendulum with a length of 31.31 meters. So I'm actually going to start with my known unknown formula table because that will help me. Maybe I'm kind of blanking on what formula is the relevant one here. So it says calculate the period of a pendulum. So I don't know the period, but I do know the length of the pendulum. And if I recall, or if I have it on my note card or I see it on the board, there's this formula that we looked at when we were doing our pendulum experiments in the beginning of the semester, that the period is 2 pi times the square root of the length of the pendulum over gravity. So I can also add to my known column the acceleration due to gravity, which is 9.81 meters per second squared. Something important to add to your note card or the toolbox on the board. So this one actually also just becomes a pretty straightforward setup because we just plug in t equals 2 pi square root of 0.31 meters over 9.81 meters per second squared, which when I run all that math out and I plug it in, becomes 1.1175 seconds, okay? But I do have to double check my significant figures. There's 2 sig figs in that number, in the 0.31. The way I've written 9.81, it looks like it has 3 significant figures, and since it is reported to you that way, you can take it as 3. But I have a limiter in the 2 significant figures quantity there. So the actual final answer, I have to cut off this number, the 1.1175 at 2 sig figs, so it just becomes 1.1 seconds. That is the answer. I keep drawing my boxes and they keep cutting out the next problem. So the next problem is pretty similar, but it's actually asking us to find the quantity of something that's within that square root that we just talked about. So let's calculate the length of the pendulum that has a period of 3.1 seconds. So if I go back to that same table I like making, that you might be thoroughly tired of by now, but, you know, deal with it. We know the period, we know the acceleration due to gravity, but what we don't know in this case is the length. Our formula still holds, but we're just going to have to do some algebra here. Whoop, that's a good square root. We're going to have to do some algebra because remember, my preference here is that you do the algebra first and then plug in numbers later, okay? So we have t equals 2 pi square root of L over G, okay? So I'm going to divide both sides of my equation by 2 pi, and I'm going to get, that t over 2 pi, the period divided by 2 pi, is equal to the square root of L over G. So in order to get rid of that square root, I'm going to square both sides, which means that I get t over 2 pi squared is equal to the length divided by gravity. So now all I have to do is multiply both sides by gravity, and I get, I'm going to draw a little arrow here to make it, big arrow, make it more clear, that now gravity multiplied by the period divided by 2 pi squared is equal to the length of my pendulum. Okay? Feel free to rewind the video and go back over my algebra here. I'm going pretty fast, but all I have to do now is plug in some numbers. So the length is equal to 9.81 meters per second squared multiplied by 3.1 seconds divided by 2 pi, and I have to square that. And that should give you my answer. And so when I plug all the numbers in and when I get just sort of the long value, I get 2.38555 and so on and so forth. Don't forget that we had units in the first place. We're asking you to find the length, so the units of this will be meters. We do need to do a sig fig check, so I'm going to look right here where I plugged in all the numbers. It looks like I have 2 sig figs in the 3.1, 3 sig figs in the 9.8. Pi doesn't matter. So my whole answer has to come down to 2 significant figures, but now we have a rounding problem because it's 2.38, and so that 8 has to round that 2.3 up. So I get 2.4 meters as my final answer that I put in a big box. So this next one's an interesting problem because it's got a lot of words in it and it seems like it's asking you for a lot, but in actuality it's not asking you for a lot. If we look at the stuff we're given here, let's do our known unknown formula table. So the sound wave has a velocity of 340 meters per second. So I know that the speed of the sound. It says orchestra instruments all tune their instruments to using A4 or 440 hertz. Oh, that's a frequency. Okay, so I know a frequency, and I don't know what they're asking me to calculate, which is the wavelength. However, I do know a formula that very neatly puts all that together. So all I have to do is solve this V equals lambda F formula for what I really want, which is the wavelength. So I'm going to divide both sides by the frequency, and I'm going to get that the wavelength is equal to the speed of the sound wave over the frequency, which when I plug that in, I'm going to do 340 meters per second divided by 440 meters per second, okay? Nothing too crazy here. So if you plug that into your calculator, you should get something along the lines of 0.772727, and that should repeat on. Now keep in mind the units, it's a wavelength, so that's meters, okay? Oh, what did I do here? Oh, I plugged in meters per second for frequency. Somebody probably caught that and started screaming at their computer. Well, kudos to you. Each of these values only had 2 significant figures. So that means my answer can only have two significant figures, which means I'm going to chug this down to 0.77 meters. That is the wavelength of that wave. Okay, everybody, we're in the home stretch here. So we have this next problem that talks about a water wave having a wavelength of 17 meters and a wave speed of about 23 meters per second. So let's do our known unknown formula table here. I feel like you all can probably guess where this is going, but I do know the wavelength and I do know the speed, but I don't know the frequency. And again, it seems to be that really handy formula, the V equals lambda F, that seems to be popping up a lot. So it says, what is the frequency? Well, I'm going to start with V equals lambda F, and I'm going to divide both sides by the wavelength to get rid of that on this side. And I'm going to reverse my equation just to make it a little easier to see. And I know that the frequency is the speed divided by the wavelength. So I'm just going to plug those values in. I'm going to plug in 23 meters per second. I'm going to divide that by 17 meters. So if I look at the units, it looks like the meters are going to go away, and I'm going to be left with 1 over seconds, which is the units for frequency. So that's nice. When I get the regular number, I get 1.3529 and so on, 1 over seconds. But if I do my sig figs, both of these values have two significant figures. So that means my answer has to come down to 2, which means that I have to round a little up. And so I get that the final answer is 1.4 hertz. Please report the final value of frequencies in hertz. Okay, don't write 1 over seconds, which means that there are about 1.4 waves per second. Okay, so what's the period of the same wave? Okay, so this is going back a little bit, but if we remember, if we dig deep, if I actually even add up here, there's another formula here that relates the period and the frequency, and that is that the period is just the inverse of the frequency. Okay, so if I know that the period and the frequency are inversely related, then I can just say that T equals 1 over F, and that equals 1 over, and I'm actually going to backtrack and plug in the longer value here, because I want to get the most accurate answer. But keep in mind, 1 over seconds is seconds, so that means that my units check out. So when I plug this number into my calculator, I get 0.739130 and so on seconds. And again, I'm going to keep in mind that I had two significant figures in the final version of that frequency. So I'm going to keep two significant figures in this final answer as well. So I'm going to get 0.74 seconds as the period of the wave. Okay, so number 7 is kind of a fun one. It's a bit of a backtracking problem. So we're asking you to draw the shock wave of a bullet that's traveling 720 meters per second. So keep in mind that the shape of the shock wave is determined by how much faster the bullet is traveling than sound. So what I really want to know here is how much faster is the bullet traveling. So I know that the bullet is traveling at 720 meters per second, and that sound is traveling at 340 meters per second. So I'm going to get the ratio here. You're going to hear a little click-clacking right now. My dog is being very clingy and interested in this video. So bear with me when he's walking up to the camera. So the ratio of the speed of the bullet to the speed of sound is 720 meters per second divided by 340 meters per second. Okay, so when I plug that into my calculator, and I'm going to do this real time. Normally I've been jumping around and not doing it real time, but what I get here is that the bullet is traveling 2.117647 times faster than sound. Okay, so what I'm going to do is I'm going to try to keep in mind, okay, when I'm given the image, like if I scroll back up to my image where I had this problem, the whole point of this was to measure the ratio of the distances, because if I look at this formula off to the right here, the ratio of the speeds should be the same as the ratio of the distances. So what I'm trying to do is build the distances. So I've got the ratio of the speeds, and I'm trying to back out some relative distances. The nice thing here is you can make up your own number. So what I'm going to say is VB over VS is the same as DB over DS. And I know that that is equal to 2.117647 and so on. I'm going to leave that number in my calculator because I like it. So here's what I'm going to do. I'm going to pick an arbitrary distance for the bullet, and then, or the sound. I think I'm going to do the sound. And then I'm just going to figure out the distance the bullet traveled. So here's what I'm going to say. I'm going to pick the distance of the sound wave. And I'm going to make that really easy on myself and say that's 1 centimeter. Okay.